Okay, this is the presentation for Team JPM's final project. I'll start off with discussing the data structures we used to implement the storage. Initially, we were using a lookup table, or actually it was a reverse lookup table, which stored a list of every address in the system and what tag was living there and what the state of that tag was. And that was pretty simple to implement, but we had some reservations that was inefficient, and especially if we wanted to split up the memory into smaller chunks, for example, to be able to use small chunks as soon as they're freed up. That could lead to storing a lot of addresses. So we wanted to come up with another approach, and the one we came up with was sort of a combination of a hash map and a linked list, which is essentially you pass it in a tag for the transaction, and it gives you back a tag descriptor, which is this struct here, and that stores it's like a linked list node. It's got a previous tag and a next tag and the state of the tag and the physical offset in memory. This was probably one of the more difficult parts of the code to implement, but it does appear to be finally working. Next I'll talk about the replacement algorithm that we used, and it was just the clock algorithm. We chose that because it's really straightforward and simple to implement. Basically, we wanted to leave open the possibility for exploring some more interesting cache replacement policies, but sort of ran out of time on that. So basically, the overall structure of the system is that it's split up into several memory regions, and each region can have, or it does have, its own replacement policy, but they're all the same. They're all the clock policy, but potentially they could each have their own policy. I'll give a demo of how the clock algorithm works, so you can see in more detail in a few minutes. Next thing I want to talk about though is the overhead of all this this storage data, or the metadata. And so what we did, we calculated for the tag descriptor that requires 18 bits, and in the worst case that there would be 32 of them, so that's 576 bits. And also we have pending read and write queues, so that's going to require some storage. So what we did, we allocated one of the M2 units, so 512 bytes, and one of the M1 units, another 128, or actually half of one of them, so another 128 bytes, for a total of 640 bytes used to store all the metadata. And that only leaves about 64 bits for the queues, which is maybe not entirely realistic, so there may be some more work to do there if to make this more realistic. What next is the so next up is the assumptions we used in building the system. So basically, we used all the available memories. So the total cost is the maximum of 170, and the reasoning there is we were just trying to maximize, or to minimize latency rather, and it didn't seem to be any. It seemed like fairly obvious that was the thing to do. So one other assumption, or one other sort of implementation detail, is that we have two buffer, two 1024 byte buffers. So basically, we give up two of the big memories just to use as input-output buffers. So you'll see in the demo that there's two of those missing, and that was just to sort of simplify the concurrency, basically, and also because writing to memory, byte by byte seemed like it was going to be pretty complicated. So basically, all of an incoming request just goes into a buffer, and then when it's finished, it goes into memory. That was mainly for simplicity. Okay. So next, I'll give a couple of demos. First, I'll go through the first traffic file. So here on the right-hand side, you can see sort of the state of the system. And right now, they're just going into the write queue as the phones are transferring the data to the hub, and then they'll start to arrive and get written into memory. You can see the big region filling up. The big region fills from bottom to top to leave open the possibility that these upper memory regions could spill into the bigger region if needed. So when it reaches the top, here it's full, and so at this point, if another one of these 1024 byte requests comes in, it's going to have to do an eviction. So it's going to look in this region and see that there's two slots, or there's enough room available for one of these big 1024 byte chunks. So it's going to reallocate and kick that up here. It's going to evict and kick that into here. And then it gets another request came in, and so this region's memory is used, so it's now uploading to the satellite. That's what this red means. And you can see the communications cost is starting to go up. And there, that's it for that scenario. I'll just go through one more, scenario 3, just to see something different. So here's traffic file 3. So one thing I forgot to mention is that these the yellow and green. So green means it's recently used, and yellow means that it's been looked at, and that's sort of the clock algorithm in action. It wraps around and marks them yellow as it's searching. So basically, this yellow one is the next one that's going to be replaced. That's it for that one. As you can see, it's a little more expensive. I'll just go show you the overall summary of the results. You can see some trends here. Traffic file 1 was 46 cents, and traffic file 2, which was the one that was, I think, almost entirely or mostly the 128 byte requests, that didn't take any satellite time, because basically it just reallocates these starting from the top. It just spills into these ones, so it never has to go to the satellite. And lastly, that you can see this one didn't work out quite as well. It's a little more expensive on the communications for that one. So that's pretty much everything I wanted to say. I think, right, okay, so there's one thing I left off, which is just how we measured the performance. So we used an event-based architecture, so basically a linked list of events, and that made tracking the latency a little more tricky. In fact, there's one bug in the linked list which is causing some of our latencies to be off a little bit. So we don't have a complete good picture of what the latency is, but having more time, I think we resolve that quickly. So that's about it.